A small metal sphere carrying a net charge of Q1 is equal to minus 2.8 microcoulomb is held in a stationary position by insulating supports. A second small metal sphere with a net charge of Q2 is equal to minus 7.8 microcoulomb and mass 1.5 grams is projected towards Q1. When the two spheres are 0.8 meters apart, Q2 is moving towards Q1 with speed 22 meters per second. Assume that the two spheres can be treated as a point charges. You can ignore the force of gravity. Part A. What is the speed of Q2 when the spheres are 0.4 meters apart? Part B. How close does Q2 get to Q1? Given the values, the charge Q1 is equal to minus 2.8 microcoulomb. 1 microcoulomb is equal to 10 to the power of minus 6 coulombs. So minus 2.8 into 10 to the power of minus 6 coulomb, and charge Q2 is equal to minus 7.8 microcoulomb, that is equal to minus 7.8 into 10 to the power of minus 6 coulomb, and the mass of the sphere Q2 is equal to M is equal to 1.5 grams. 1 gram is equal to 10 to the power of minus 3 kg. So 1.5 into 10 to the power of minus 3 kg. And the speed of the charge Q2 at initial position 0.8 meters apart between the two charges is the speed Vi is equal to 22 meter per second, and the distance between the two charges initially at Ri is equal to 0.8 meters. This is the given values, and draw the figure. The sphere Q1 is placed at stationary. This is the Q1, and another sphere moving towards the Q1. This is the charge Q2. The charge Q2 is moving towards the Q1. The distance between the two charges is the initially 0.8 meters. This is the Ri, initial distance between the two charges Q1 and Q2. At that position, the speed is Vi. The charge Q2 speed Vi is equal to 22 meter per second. This is the initial position. First of all, part A, we can calculate the speed of the charge Q2. The distance between the charge Q1 and Q2 is 0.4 meters, where this is the RF. This is the final distance between the charge Q1 and Q2, 0.4 meters. So at that distance we can calculate the speed of the charge Q2. So let us consider this is the distance between the two charges Q1 and Q2. Finally, this is the 0.4 meters apart, Q1 and Q2. In this distance, in this point, we can calculate the speed of the charge. This is the Vf. We can calculate the speed of the charge Q2 at a distance 0.4 meters from the Q1. So from this, the charge Q1 is stationary, does not have the kinetic energy. The charge Q2 is moving towards the Q1. So the charge Q2 has the kinetic energy. From this figure, first of all, we can calculate the energy at the initial position 0.8 meters from the Q1. So at the initial position, the total energy is the Ui, where Ui is the initial total energy of the charge Q2, the distance from the 0.8 meters from Q1. So this is the initial energy, total energy. The charge Q2 have the kinetic energy and electrostatic potential energy. So the initial total energy is Ui is equal to Ke initial. The charge Q2 have the initially kinetic energy is the Kei plus initial electrostatic potential energy is the Pei. So Ui is equal to the kinetic energy of the Kei is equal to half mvi square. This is the initial kinetic energy of the charged particle Q2. So Kei is equal to half into m is the 1.5 into 10 to the power of minus 3 kg and into the velocity of the initial charge Q2 is 22 meter per second whole square. So the total kinetic energy is Kei at a point initial, that is equal to 0.3630 joules, and we can calculate the initial electrostatic potential energy of the charged particle P2. This is the Pei is equal to K Q1 Q2 by Ri. So Pei is equal to, this is the initial electrostatic potential energy of the charged particle Q2 and Q1, where K is the electric force constant. The value is the 9 into 10 to the power of 9 Newton meter square by Coulomb square, into where Q1 is the minus 2.8 into 10 to the power of minus 6 Coulomb, into Q2 is the minus 7.8 into 10 to the power of minus 6 Coulomb, whole by the distance between the two charges initially is 0.8 meters. So the initial electrostatic potential energy Pei is equal to 0.2454 joules. This is the electrostatic potential energy of the two charged particles at a distance between the 0.8 meters. So the total energy of the charge Q2 at a distance 0.8 meters is the Ui is equal to Kei plus Pei, where Kei is the 0.3630 joules plus Pei is the 0.2454 joules. So the total energy Ui is equal to, this is the total energy of the charged particle, that is equal to 0.6084 joules. This is the total energy of the charged particle Q2 from distance between the two charges is the 0.8 meters, and we can calculate the energy of the charged particle. The distance between the two charges is the 0.8 meters from the two charges is where this is the final energy UF. So we can calculate the total energy of the charged particle Q2 at a distance 0.4 meters from the Q1. So in this point, the total energy is the UF is equal to the kinetic energy This is the KEF plus the electrostatic potential energy is the PEF. This is the point 0.4 meters from the Q2. The Q2 is moving towards the Q1. So the distance between the two charges is 0.4 meters. In this case, the electrostatic potential energy PEF is equal to K Q1 Q2 by RF. So the electrostatic potential energy EPF is equal to K is the 9 into 10 to the power of 9 Newton meter square by Coulomb square into Q1 is the 2.80 into 10 to the power of minus 6 coulombs into Q2 is the minus 7.80 into 10 to the power of minus 6 coulombs whole by, where RF, the distance between the two charges, is finally 0.4 meters. So PEF is equal to, this is the electrostatic potential energy, final distance 0.4 meters is the 0.4907 joules. This is the potential energy of the charged particle between the two charges, and the distance is 0.4 meters apart. So the total energy is the UF is equal to KEF is the half mVF square plus PEF is the 0.4907 joules. This is the total energy of the charged particle Q2, the distance from 0.4 meters from the Q1. So according to the conservation of energy, the initial energy is equal to the initial energy UI is equal to the final energy at a point UF. So from this equation, initial energy is the 0.6084 joules. The final energy is the half mVF square plus 0.4907 joules. From this equation, the initial energy is the 0.6084 joules is equal to, the final energy is the half mVF square plus 0.4907 joules. From this equation, half mVF square is equal to 0.6084 joules minus 0.4907 joules. From this equation, half mVF square is equal to 0.111177 joules. So from this equation, the final velocity of the charged particle at a distance 0.4 meters between the two charges is the VF is equal to, cross multiply the equation, 2 into 0.1177 joules whole by m into square root. From this equation, that is equal to 2 into 0.1177 joules whole by, where mass m is the 1.5 into 10 to the power of minus 3 kg whole root. So the velocity of the charged particle Vf, this is the final velocity of the charged particle at a distance 0.4 meters is the, solving the equation, the value is Vf is equal to 12.5 meter per second. This is the velocity of the charged particle. This is the velocity of the charged particle at a distance 0.4 meters from the charge q1. So this is the final velocity of the charged particle. Consider the part B. The part B is the how close does q2 get to q1. So in this case, this is the charge q1, this is the charge q1, and the initial charge q2 at a point, the distance between the 0.8 meters from the q1. At that distance, the initial velocity is the 22 meter per second, and the case 2 or the part B means the distance between the two charges, the nearest distance between the q1, we can calculate the nearest distance between the q1 and q2. At that distance, the final velocity is 0. So let us consider the charge q2 moving towards the q1 at some position. The final velocity at that position, the final velocity Vf is equal to 0. This is the final velocity. We can calculate the distance between the two charges is the r. So we can calculate the distance between the nearest distance between the two charges. At that distance, the final velocity is 0. So the initial velocity of the charged particle at a distance between the two charges 0.8 meters is the ui. Ui is equal to, we already know that the initial velocity of the two charges is the distance between the two charges is the 0.6084. This is the, we can calculate the initial energy of the two charges, and the final velocity of the charge at a distance r. This is the uf. In this case, uf is equal to only the electrostatic potential energy is there, the kinetic energy is the 0. So in this case, the electrostatic potential energy EPF plus the kinetic energy is also 0, because at this nearest distance, the kinetic energy is 0 because the velocity of the charged particle is 0. So according to the conservation of energy, so the electrostatic potential energy is the UF is equal to the electrostatic potential energy is the K Q1 Q2 by R. So according to the conservation of energy, the initial total energy UI is equal to the final total energy UF. So in this case, the initial energy is the 0.6084 joules is equal to the final energy is the K Q1 Q2 by R. Multiplying the equation, from this equation, the distance R is equal to K Q1 Q2 by the value is the 0.6084 joules. Substituting the values, where R is equal to K is the 9 into 10 to the power of 9 Newton meter square by Coulomb square into Q1 is the minus 2.8 into 10 to the power of minus 6 coulombs into Q2 is the minus 7.8 into 10 to the power of minus 6 coulomb whole by the value is the 0.6084 joules. From this equation, where R is equal to where r is equal to, solving the value, r is equal to 0.323 meters. This is the distance between the two charges, 0.323 meters at the nearest distance between the two charges. At the distance, the final velocity of the charged particle is 0.